All right, we are now recording. Share the screen. All right, so as I mentioned in the Canvas announcements just before we started, so let's go ahead and set the exam 4 as being Thursday the 22nd. Let's set exam 5 as Thursday, May the 13th. And the final exam for Thursday the 20th. But all these other dates are tentative. They're still kind of fluid. Okay, last time we left off at 15.5. Okay, so 15.6, which on the original schedule was supposed to be here. So I'm about a day ahead, I think. Okay, not that much more. You might think we're way ahead, but we're not because, again, trying to shift everything up. Okay, so my goal for this week is 15.6, 7, and 8 on the triple integrals. Okay, and that would leave 15.9. So we should be done with chapter 15 in plenty of time, and hopefully I can even get started with some of chapter 16. Okay. All right, so we'll be doing triple integrals. They can get really long. Okay, and I'm aware of that. In fact, some of the problems myself, I started to do it and I said, no, I don't want to do it anymore. It's too long. Okay, and of course, that's something I have to keep in mind when I construct the tests for you guys. And yeah, reminder, I'm planning all the other exams from here on out are going to be the entire class period. So you have the entire class period for exam 4, exam 5, and of course for the final exam. Okay, so we left off before the spring break here, 15.5. So 15.6 is on triple integrals. Okay, 15.7 and 8 are also triple integrals, but in different forms. Okay, this is on something called cylindrical coordinates. This is on spherical coordinates. So if I can get to 6, 7, and 8, we'll be good. Okay, I do plan to give you a quiz on Thursday. It'll be on triple integrals. I'll give you a quote unquote easy triple integral, and we'll see how that goes. Okay. All right, so the rest of these calendar dates aren't set in stone, but we are going to set the exam dates. Okay, so the 22nd for exam 4, Thursday the 13th for exam 5. So what's going to happen on the 18th? It'll just be a question and answer review type of session. If you have questions about anything or previous exams, that's pretty much just going to be it. And then we have our final exam on the 20th, and then we're done. Okay. All right, so any general questions before I get started with the new stuff on triple integrals, 15.6. And again, fortunately, before the break, I snuck in enough of 15.6 so that it should make things a little bit easier today. Okay, so any quick questions before we go on? Okay, we only have about 7 weeks left. We're on this side of the paper now, so we're done with all this. So we're more than halfway. All right. Okay, so we'll go ahead and get started with triple integrals. So 15.6. So triple integral f of x, y, z dv over a region B, B standing for a box, that's the easiest. Box meaning they're all constants. X is going a constant this way, y is constant this way, z is constant this way. dv has 6 forms, dx, dy, dz in some order. Okay. Again, why is it 6 forms? You have 3 choices for the first letter. Once you place on the first letter, you have 2 choices for the next. And then once you place that down, you only have 1 choice for the last one. So 3 times 2 times 1, or 3 factorial. If you had 4 variables, x, y, z, and t, then you have 24 ways, 4 factorial, possible ways to mix them all up. All right. And Fubini's theorem says if you have constants, constant here, 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 it's a box. And please notice the notation, A, B cross C, D cross RS. This is for X, this is for Y, this is for Z. Okay, so you could have dx, dy, dz. If it's dx, dy, dz, then these are for X, these are for Y, these are for Z. It goes inside out. Okay, our favorite, quote unquote, is dz, dy, dx. Okay, and why is it our favorite? You say, well, it's not my favorite. Well, you know, we've been doing z as a function of x and y, so it's good to get that out of the way. Then once that out of the way, do we do y as a function of x or x as a function of y? We usually do y as a function of x. So then dy would be next and then dx last. So our so-called favorite is dz, dy, dx. But technically you can have 6 orders, right? 3 choices for the first variable, then 2 choices for the second variable, and then no choice for the last variable, 3 times 2 times 1. Okay, so again, it works inside out. So if it says dx, x is going from A to B. Okay, if it's dy, y is going from C to D. And then dz, z is going from R to S, inside out. Okay. Now you can change it. So if it says dz first, then these inside numbers have to be what? R to S, right? And then dy would still be C to D, I guess. Then dx would be last, and then the outside one would have to be A to B. Is that right? So it goes inside out for Fubini's theorem. Okay, so that's pretty easy. Now, what about in general? Okay, the general triple integral f of x, y, z, dv be something like, well, what's most useful is number 7, page 1031. Okay, so they have our favorite, dz, dy, dx. Again, it doesn't have to be in that order. But the rule is the inside variable can be a function of the other 2 letters. So dz, you could have a function of x and y here and a function of x and y there. In fact, I don't know if you can see it there. Yeah, see on the inside it says u1 and u2 of x and y. Then the middle one, dy, can only be a function of x. So in the middle, they say g1 of x and g2 of x. And the outside one always has to be just constants, a and b. Okay, so the easiest case scenario is when you're integrating over a box region, that means they're all constant, right? Constantly, x is from one number to another number, y is from one number to another number, and z is from one number to another number. But it's more complicated when you have regions like this or whatever, right? Okay, so they changed this one. They have dz, dx, dy. So dz, that means z can be a function of x and y. Then dx, so x can be a function of y. Obviously, we're not as comfortable with that. But this outside one, the first one, always has to be numbers, C to D. Okay. All right, and let's see. This one on page 1034. Volume can be thought of the triple integral of 1 dV, right? So they ask you to find a volume. One way to find a volume is integrate 1 dV. Okay. By analogy, double integral of 1 dA is A. Single integral of dx is just the length of the interval. So you just keep adding up one dimension. So I've been saying before, right, integral of dx is length of interval. So let's say integral from A to B, right? Then the length of interval is just going to be B minus A. That's one dimension. In 2 dimensions, double integral of 1 dA gives you the area. 3 dimensions, triple integral of 1 dV gives you the volume. Okay. All right, so here we go. So 15.6. So we had 1 to 21 odd except skip 15. I think I actually started 15, but it got to be too messy. So I said, if it's too messy for me, I'm not going to make you do it either. Okay, so just 1 to 21 odd, or I say just, but triple integrals can get really long, really bad, as you might guess. Well, minimally, it's 3 integrals in one, right? In one problem. So one problem has 3 integrals. So that's just like doing 3 separate integrals in Calc 1, right? Okay, so this is for the benefit of those who don't have the book and aren't getting it. Page 1037. So just that. Okay, starting with 9, they don't give you the integrals directly. You have to figure it out, so to speak. 13, 15. And then, what do we do? 17, 19, 21, I think. 17, 1921. Okay. So there we go. All right. Number one, well, let me show you the directions. Evaluate the integral in example one, integrating first with respect to y, then z, then x. So I never liked it when the author makes you take a problem and then turn back to a different page for the rest of the problem. You guys know what I mean? So you got to keep flipping back and forth. Example one. So we're integrating x, y, z squared. And the box, x goes from 0 to 1, y goes from -1 to 2, z goes from 0 to 3. Okay, they went dx, dy, dz. I might be able to get this. This is where it'd be handy to have a third hand, but so dx, dy, dz comes out to be 27/4. Okay, so by Fubini's theorem, I integrate any of the other methods. And by the way, that's only true if you have just constants. Okay, so any of the other 5 methods, I should still get 27/4. Okay, so here they tell me to go what? Y first, and then z, and then x. So here we go. Same function, x, y, z squared, dy, dz, dx. So if that's the order, y goes first. So if you look at the problem, y went from -1 to 2. It's not necessary to put the x, y, and z, but I'm doing it for teaching purposes to make sure you know it makes a difference where these numbers go, right? And then it says z next. So z, they told us, went from 0 to 3. Then x is last. X goes from 0 to 1. Okay, technically you don't have to write the y, z, or x. It's never wrong. It's just to remind you what to plug in. Now, when I get to this stage, I actually like to plug in because you have so many variables. You have to make sure that you don't plug into the wrong one. All right, so when I integrate dy, that means you have to pretend x and z, and therefore z squared are constant. It's constant times y. So leave alone x, z squared, and you have y squared over 2. Okay, and then y equals 1 to 2. I like to write y equals 1 to 2 because that tells me, right, you get so many letters. Oh yeah, what am I plugging in? Oh yeah, I'm plugging in for y, not for x, not for z. Now, when you're doing single variable calculus, right, like calc 1 and calc 2, you obviously didn't have to put down the y equals because there was only one letter, right? The only game in town was x or y or theta, but now you got so many letters, okay? I think it's wise for teaching purposes and also for me, since I'm getting C now and all that, right? That say, now what am I plugging in for? I got all these letters. Oh yeah, y equals 1 to 2. Okay, you're allowed to factor out the half. So I plug in 2, I get 4. Plug in 1, I get 1. So it's 4 minus 1, which is constant. Take that out, and I'm still left with xz squared, right? So 0 to 3 for z, and 0 to 1 for x. Okay, plug in 2, you get 4. Plug in 1, you get 1. Half is out, so that becomes 3 over 2. Okay, integrate with respect to z. That means x is constant. So constant x, z cubed over 3. Z equals 0 to 3. Plug in 0, you get 0, so forget about it. Plug in 3, you get 9. 9's a constant, take out the 9. So 3 halves times 9, integral from 0 to 1 of x dx. All right, so then we're home free. So that becomes 27/2. Integral of x is x squared over 2. Notice I didn't put x equals here because it's obvious. It's only one letter, right? I might get mixed up here and here because there's so many letters, right? If I just put the 1 and 2, now what am I plugging in again for x or y? So, oh yeah, y equals, because there's 3 letters. When I finally got rid of y, here I still got 2 letters. So I still want to put z equals 0 to 3. Otherwise, if I don't put it, now what am I plugging in again? X or z? Here it's obvious, right? There's no other letter. It's only x. Okay, plug in 0, forget about it. Plug in 1, 27/4. Okay, so that's my final answer. All right, so that's the way it goes. Okay, problem 5. Yeah, you can see I messed up. That should be a 2z, I believe. Let's take a look. Question number 5. The top middle one is 2z, right? x e to negative y dy dx dz. before going on, let's think of the rules of the game. dy. These two are allowed to have what? X and z. They don't have to, but they're allowed to. There's an x, there's no z, that's okay, and that's a number, that's okay. This one is x. So what are these allowed to have? Z. There's a 0, there's a 2z there. And then, of course, what helped me catch is I first put 2x. I said, wait a minute, that's not even allowed, right? You're only allowed to have z. But the outside always, whether you have a single integral, double, well, single integral is obvious, double integral, triple integral, quadruple integral, this outside one must always be numbers, 1 to 2. Okay, so here we go. So what's the integral of x e to the negative y? X is a constant. Integral of e to the negative y is negative e to the negative y. Okay. Plug in ln x. For y, I have x e to the negative ln x. And watch out, when you plug in 0, you do not get 0. Okay, so sometimes I get students who say, oh yeah, 0, it's automatically 0. Not here, watch out, you get e to the 0, which is 1. So you're gonna end up with an x also. So it's x e to the negative ln x minus x e to the 0. You know, e to the 0 is 1. How do I clean this up? Now, at first you might say, oh yeah, e and ln cancel out, but there's a negative in a way. To get rid of that, take that -1 coefficient and make it come up. Remember that property of logs, right? If you have -1 here, you can make it come up here. So you have x to the -1. Then the e and the ln can cancel out, which is x times x to the -1, x times 1 over x, which is 1. Very nice. Okay. So in other words, all of this stuff is now 1 minus x, dx dz. Okay, now what did I do here? I have that negative there, so I decided to distribute the negative back in and turn that around and make it x minus 1. Right, the opposite of a minus b is b minus a. Remember that from algebra? So I don't have the negative anymore. So I'm integrating x minus 1 dx dz. All right, so that's x squared over 2 minus x. As x goes from 0 to 2z, plug in 0, you get 0, so forget about it. Okay, plug in 2z, let's see, that's 1/2 of 2z squared. 2z times 2z is 4z squared minus 2z dz. Okay, so I have integral of 2z squared minus 2z dz. Okay, now I just have a single integral, so I'm good. All right, so 2z cubed over 3 minus z squared from 1 to 2. Plug in 2. 2 times 8 over 3, 16 over 3, minus 2 squared is 4. Subtract, plug in 1, you have 2/3 minus 1. And what did I do here? I distributed 16/3 minus 2/3 is 14/3. And then -4 minus a minus 1 is -3. So it's 14/3 minus 3, 14/3 minus 9/3. Final answer is 5/3. So that's the way it goes. Okay, and keep in mind now, these are regions we're integrating in space. The easiest ones are boxes. So how do you know what's a box? Everything's a constant. X, front and back, from 0 to 1. Z, up and down, 0 to 3. Y, left and right, -1 to 2. But you could have more fancy stuff like this and like this. So you're integrating over a 3-dimensional shape. Okay, so you can integrate over all kinds of stuff, which now makes integrating in Calc 1 very ordinary, right? What? All you're doing is we're only integrating from A to B on a line segment, right? It's like, is that all? Right, now we're integrating over 2-dimensional and 3-dimensional objects. Right, now, starting with problem 9, they do not explicitly write integral out for you. You have to figure it out. Okay, but as I mentioned the Thursday before the spring break, some of these you can tell right away. And by the way, if you can't, then if it doesn't make any difference, you can just pick what you want. But I think I talked about this before the break, right? So number 9, by the rules of the game, what has to come first, second, and third. Okay, so look at that, that, and that. So what has to be first? Z, it has two variables. What has to be next? Y, it's got an X in it. And X only has constants. Okay, so this one must be dz, dy, dx, which was going to be our favorite anyway. Okay, keep in mind, I know it's hard to visualize this. You can do this in a computer simulation, I suppose, if you wanted to. But this defines a three-dimensional space, right? Z lying between that and that, Y between 0 and X, X between 0 and 3. Whatever it looks like, we're integrating the function Y dv. Right, so by the rules of the game, we say it must be Z first, then Y, then X. How come? Z has the other two letters, X minus Y, X plus Y. Y had the other letter X. Y is not allowed to have Z. You're done with Z. And the outside X is constant. Okay, and once you have that, that's pretty straightforward. Okay, now again, the shortcut. Integral of Y dz. As far as Z is concerned, Y is a constant. So it's just going to be Y times the length of the interval. X plus Y, subtract X minus Y. Take advantage of those shortcuts. It's much, much easier, especially when you get to triple integrals. I mean, you're happy you don't do any quadruple integrals where you have to integrate with X, Y, Z, and T, let's say. Okay. So that goes along with what we said about, integral of 1 dx is just the length of the interval. I just wrote that a moment ago, I think, didn't I? Put it in my book, right? Page 1034, I wrote it. Integral of 1 dx is the length of the interval, b minus a. So the integral of y dx, y is constant, it's y times top minus bottom, x plus y minus x minus y. Okay, if you work this out, x minus x is 0, y minus a minus y is 2y. So I have y times 2y, which is 2y squared, dy dx. And again, you should know right now when I say dy dx, that isn't the thing that looks like dy over dx, the derivative, right? It's the integration dy times dx. Okay, that should be pretty easy. By the way, here you might say, well, these are constants. Can I just take the length of the interval 3? The answer is no, because this one is not constant. Okay, there's going to be an x involved in my last integration, as you can see over here, right? So 2y cubed over 3 from 0 to x. I didn't put the y equals here, but in this case, it's kind of obvious. Plug in 0, you get 0, forget about it. So I have 2/3 x cubed, integrating from 0 to 3. All right, then I'm pretty much home free. So 2/3 x to the 4th over 4. Plug in 0, you get 0. Plug in 3. Let's see, 2/3 times 1/4. 2 cancels the 4, that gives me 1/6. Times 3 to the 4th power, 81. 27 over 2 is my answer. Okay. All right. So let's try 13. Integral over E, 6xy dv. E is some region. Okay, under the plane of z equals 1 plus x plus y, and above the region in the xy plane. Xy plane means z equals 0. Okay, so z is going from 0 to 1 plus x plus y. And then bounded by these curves here. Okay, so one more time. If it's the region above the xy plane means z equals 0. Okay, and then I'll show it to you, but I wrote down all the other stuff. Z equals 1 plus x plus y, bounded by the xy plane, that's z equals 0. Okay. And then they told me bounded by all this other stuff. Y equals radical x, y equals 0, x equals 1. So there we go. So z is going from 0 to 1 plus x plus y. Two variables must be first. What has to be next? Y. Y goes from 0 to radical x, something involving x. And then they said x goes from 0 to 1. Okay, so that clinches it. So the function was 6xy dv. dv, again, is our favorite. Yeah, whenever we have the chance, we'll do our favorite. What's our favorite? dz, dy, dx. Z is a function of x and y, although strictly speaking, it doesn't have to be. You can have y as a function of x and z, and you can have x as a function of y as z. We'll have very few of those. That's just like in Calc 1 and 2, right? You almost always had y as a function of x. Once in a while, we did x as a function of y, but that wasn't our favorite. So in a similar fashion, our favorite, so-called, is z as a function of x and y, but you don't have to. Okay, z goes from 0 to 1 plus x plus y. Y goes from 0 to radical x. X goes from 0 to 1. Okay. So there we go. Now, again, please take advantage of shortcuts. You're integrating dz first. If dz is first, what does that make 6xy? Constant. So it's constant times the length of the interval. 6xy times 1 plus x plus y minus 0. So go straight to 6xy, 1 plus x plus y. Save yourself some time and energy in doing that. I don't feel like writing it because it's too much writing. But if you really don't like it or you don't get it, okay, I'll just say it, but I don't feel like writing it. If I integrate dz, when you integrate, it'd be 6xyz, right? Do you agree? 6xyz. You would plug in 1 plus x plus y. There it is. Then you plug in 0, which is 0. So there it is. It works. Okay, distribute 6xy times 1, 6xy times x, 6xy times y. Oh, I'm sorry. I actually factored out to 6. That's right. That's better. Factor out to 6. xy plus x squared y plus xy squared. dy dx. Okay, so I'm integrating with respect to y. That means x is constant. xy squared over 2. X squared is constant. Y squared over 2. X is constant. X, y cubed over 3. Y goes from 0 to radical x. Is it true when you plug in 0 for y, you get 0? Yes. So again, don't bother writing it. It'll be too long. Okay. Now, I'm going to plug in, but I notice all of these have fractions. I don't like fractions. There's a 6 out here. So I'm going to change that to 3, change the second one to 3, change that to 2. That's legal, right? First I factored out a 6, then I noticed, oh man, I got all these fractions. So wait a minute, I can get rid of the fractions if I go 6 divided by 2 is 3, 6 divided by that 2 is also 3 in the middle, and 6 divided by 3 is 2. No more fractions. Okay, plug in radical x for y. You have radical x times radical x, which is x. X times x. So I have 3 times x times x. This would be 3x squared radical x times radical x. This would be 2x, then radical x cubed. Radical x cubed is radical x, radical x, radical x, or x radical x. Okay, so that becomes 3x squared. That's 3x cubed. 2x times radical x is x to the 5 halves. X to the 1 plus 1 plus a half. So finally I have something I can work with. And now it's just an ordinary garden variety integral of one variable. So x cubed, 3x to the 4th over 4, 2 times, this is a little bit sloppy, x to the 7 halves, right? Add 1, 7 halves, divided by 7 halves means times 2 7s. from 0 to 1. Plug in 0, you get 0. Plug in 1, that's 1, that's 1, that's 1. So you just have the coefficients basically. 1 plus 3/4 plus 4/7. Common denominator is 28. 28 over 28. Multiply by 7, multiply by 7, 21. Multiply by 4, multiply by 4, 16. Final answer is 65 over 28. Okay, I'm done with that side. Let me do my focusing thing again, in case you weren't able to focus that. So here's all of this. Yes, I know I'm going fast, but you can always pause the video. Oops, there's that. And then over here, some more and some more. And there we go. Okay. All right, now, I know I actually threw out problem 15. I'm going to show you part of it anyway, just to show you what happened. And it's a nice setup, but just after a certain part, it's just a mess. Okay, but let me show you a technique that you may want to know. So in other words, I think it's worth it to take notes on this anyway, even though it's technically not assigned. (15) Triple integral of t y squared dv. T is a solid tetrahedron with vertices origin 2, 0, 0, 0, 2, 0, 0, 0, 2. Here's the tetrahedron that you're integrating over. By the way, it's not just the outside, it's everything inside also. Okay. Later, we'll just do surface integrals in our last chapter. Okay. 16 point something. We'll be doing surface integrals where we're only integrating over the surface. But here we're integrating over the entire solid, including the outside. So 2, 0, 0, 0, 0, 2, 0, 2, 0. So in order to do this, I have to come up with an equation of this plane. Now we can do it with cross products and so forth. Okay, that's very long and very tedious. We don't feel like doing that. Okay, instead, we know it's a plane. Planes look like ax plus by plus cz equals something, right? So the general rule is you're allowed to arbitrarily make this any number that you want. Okay, a good guess would be the least common multiple of these two numbers, of these numbers here, 2, 2, and 2. So the best number to pick is 2. Okay, if that didn't make sense, if this was say 2, 3, and 4, I would pick the 12. I'll make the outside number 12. It may not end up being 12, but it's a good start. The least common multiple. Okay, then what you do to solve for each of these is you plug in. Okay, technically you can make this anything. You know, I'll go ahead and say it, not that I'm going to do it, but you can make this pi, it would still work out, but it'd be crazy to make that pi, or 316,521 would also work. Okay, but the nicest thing to pick is the least common multiple of these three numbers, 2, 2, and 2. So ax plus by plus cz equals 2. So how do you find a, b, and c? I plug in. So 2, 0, 0 means put a 2 here, 0 here, 0 here. 2a equals 2, that means a equals 1. Similarly, 0, 2, 0 means put a 0 here, 2 here, 0 here. That means 2b equals 2, that means b equals 1. And by the same logic, if I plug in 0, 0, 2, put a 0 here, gone. Put a 0 here, gone. Put a 2 here, 2c equals 2, c equals 1. So a, b, and c are on 1. Therefore, my equation is x plus y plus z equals 2. Okay, so if they give you all 3 points on the x, y, and z axes, this is usually faster than doing what we did several chapters back, where you can find the equation of plane by finding a vector here, cross product gives you a normal vector. That's too long, and a lot of us probably forgot how to do that. But there it is, x plus y plus z equals 2. And a quick double check. If this works, do all three of these work? They certainly do. Clearly they do, right? 2, 0, 0 works, 0, 2, 0 works, and 0, 0, 2 works. But if I'm going to write it in our favorite is z as a function of x and y. So z is equal to 2 minus x minus y. Okay, so that'd be my inside integral. Then what do I do next? Okay, after that, you have to take this region in the xy plane. Okay, pretend z is 0. See this triangle over here? So how do I think of it? That's the origin. So this is a regular x and y. 2, 0, 0. Ignore the z, it's 2, 0. 0, 2, 0. Ignore the z, 0, 2. So y goes from here to here. Okay, a little bit of algebra. Y equals 2 minus x. Slope is negative 1. Y-intercept is 2. So y equals negative x plus 2, or y equals 2 minus x. All right, so now I'm ready. So I'm integrating y squared dv. dv, I'm going to go z going from 0 to 2 minus x minus y. Y goes from 0 to 2 minus x. And x goes from 0 to 2. Okay, I thought it was going to be a nice problem. It isn't. Okay, it starts out okay. Y squared is constant with respect to z. So y squared times length of the interval. What's the length of the interval? 2 minus x minus y. Distribute 2y squared minus xy squared minus y cubed. Okay, and then I decided it was too long. I put too long here. 2y cubed over 3 minus xy cubed over 3 minus y to the 4th over 4. Y goes from 0 to 2 minus x. These are zeros, but 2 minus x here cubed, 2 minus x here cubed. Okay, forget it. So it came out to be too long. So there we go. All right. What time is it? I'm actually almost done with this section. $17. Triple integral of e x dv, where e is bounded by the paraboloid x equals 4y squared plus 4z squared, and the plane x equals 4. This is not our favorite, but we're stuck. X is a function of y and z. That means I have to have x first. And x equals 4. Okay, triple integral of x dv. Now, x equals 4y squared plus 4z squared. That's considered the lower function. X equals 4 is the upper. You're probably more used to it with z as a function of x and y. I can't draw it very well. But z as a function of x and y would look like this. Z equals 4. Z equals 4x squared plus 4y squared. That's the lower, that's the upper. Turn it, and you can't really do it here, okay? But the idea is that this bow is coming out at you. Here's x equals 4. Okay? So the lower function, that says lower, and that's upper. You can tell I messed up, I switched it at first. Okay, so the lower is, by analogy, 4y squared plus 4z squared. The upper is x equals 4, so that's how I'm integrating. Okay. Now, where do they touch? Where does that touch that? We'll plug in 4. 4 equals 4y squared plus 4z squared divided by 4. Y squared plus z squared equals 1. That is our unit circle in the YZ plane. Okay. In fact, the YZ plane is the plane of the paper, as it were. because X is coming out at you positive and going in as negative. Okay, so here's the YZ plane. Since I have this, it makes sense to switch over to polar coordinates. Okay, and looks like I left off a dx here, sorry. So I'm going to integrate x is going from 4y squared plus 4z squared, which is 4r squared. Y squared plus z squared equals r squared. Okay, so here's a case where if x is a function of y. Now you said, I thought x squared plus y squared equals r squared. Yeah, that's what we're more comfortable with. But remember, you could switch around, you know, where y squared plus z squared, y and z can be thought of. In fact, the picture even shows it, where y squared plus z squared equals 1. So x is going from 4r squared to 4. And then dA after that is r dr d theta. Okay, so r is going from 0 to 1, theta is going from 0 to 2 pi. All right, so that we're going to be okay, except I messed up a lot here. So that's 4r squared, that's 4. There's no theta anywhere, no theta there. So I can take out d theta, the length of the interval is 2 pi. Okay, so let's see. See, what do I have? R x squared over 2 from 4r squared to 4, sorry. Okay, integral of x, r is constant, x squared over 2, 4 to 4r squared. Yeah, I messed up like crazy here. Let's see what happened. That 2 cancels that 2, so I have a pi. There's an r in front. Plug in 4, I get 16. Plug in 4r squared. 4r squared squared is 16r to the 4th. Okay, so I think I'm okay now. So that becomes 16, factor out the 16 pi. And then I have r minus r times r to the 4th, r to the 5th. All right, so 16 pi, r squared over 2 minus r to the 6 over 6 from 0 to 1. Plug in 0, you get 0. Plug in 1, you have 1/2 minus 1/6. Okay, 1/2 minus 1/6 is 1/3. That's 3 over 6, right? 3 over 6 minus 1/6 is 2/6. 16 pi over 3. Okay, so again, yeah, I botched this up completely, but integral of x is x squared over 2. Okay, plug in 4, not 4r squared. So 4 squared is 16. 4r squared is 16r to the 4th. So there we go. All right, so why don't we take our usual break now? I only had one more problem to show you, which was 19. And then I'll be able to get started with the 15.7. Okay, but yeah, the quiz on Thursday, I'll give you a triple integral. I'll give you only one triple integral, but of course the triple integral is long enough as it is already. Okay, so let's break into our usual time of about, what, 7:10-ish? Okay, all right, so break until 7:10, please. All right, folks, let's pick up where we were. So I'll finish this section pretty quickly, and then we'll go on to the next section on cylindrical coordinates. It's really not that big a deal. It's just a higher dimension of polar coordinates. Okay, those of you that came late, I got you. So yeah, anytime you join late, just put your name in the chat and I got you, so I got all that. About the exam, longer problems. Yeah, so I don't know if I'm going to give you 10 problems. I'm still leaning toward 10 problems, but to make up for the length of time that these problems take, that's the reason why I'm giving you the entire class period. Yes, I know that they're really long. I mean, the one problem that I started to set up for you, 15, I mean, that can still be done. It's just really long. I didn't think it was going to be that long, but it ended up being that long. And the last one I was going to do was 19. That one ended up being longer than I thought also. And it's confirmed by the fact that I messed up, but you know, what else is new there? Yes, we're having a quiz on triple integrals on this section on Thursday. And let me see, what else do I have? I think I'm caught up with the chat there. Okay, all right, so I'll do one more problem and then I'll get started with cylindrical coordinates. But it's really just polar coordinates plus add on the z. In fact, the problem that I had just done, problem 17, that's essentially a cylindrical coordinates type of problem, as it were. Okay, so let me get back to sharing the screen, please. Whoops. Okay, there we go. So this one, where we switch over to polar, that's an example of cylindrical coordinates. Okay. All right. So 19 was the last one I was going to do. Use a triple integral to find the volume of the given solid. The tetrahedron enclosed by the coordinate planes and the plane 2x plus y plus z equals 4. Okay. So remember, if you're trying to find volume, it's the integral of 1 dv. So basically just integrating dv. I have to figure out how to set it up though. All right, so the best way to do this is just draw yourself a quick picture. Okay, so we have this. So get the x, y, and z intercepts. So y and z are 0, 2x equals 4, x is 2, 2, 0, 0. Double check 2 here, 0, 0, that works. 0, 4, 0. Okay, y axis means x and z are 0. Cover these at y equals 4. And likewise, z axis means x and y are 0, z equals 4. So the points are 2, 0, 0, 0, 0, 4, and 0, 4, 0. Okay, and technically you can do x as a function of y and z, and y as a function of x and z, but we like z as a function of x and y. So solve for z, that's easy, 4 minus y minus 2x. Okay, so when I integrate, z is going to go from 0 to 4 minus y minus 2x. Okay, and to find volume, again, you just integrate dv, or 1 dv. And I have our favorite dz, dy, dx. Now, how do you figure out what happens in x and y? That's where you have to go back to the x, y plane, sort of like this problem here. So this was a nice setup. So again, this, in fact, if you kind of pretend you tilt your head and look right there, that kind of looks like your traditional x, y plane, right? This is x. It used to be going out, but now it's going to the right. And there's y going up, right? If you kind of imagine that you're looking at that funny angle. How do I label the points? Just ignore the z equals 0. So 2, 0. So that point matches that point. Okay, I'm in the xy plane, i.e. z equals 0. So ignore the z equals 0, 2, 0. 0, 4, 0, ignore that, 0, 0, 4. Y-intercept is 4. Slope is negative 2. I trust you can do that. Y2 minus y1 divided by x2 minus x1, right? 4 minus 0 divided by 0 minus 2. So y is 4 minus 2x. Double check, plug in 2, you get 0. Plug in 0, you get 4. Okay, so z goes from 0 to 4 minus y minus 2x. Y goes from 0 to 4 minus 2x. X goes from 0 to 2. Okay, again, that's our favorite. And you don't have to do that, but that makes it easier on everybody. Okay, I thought it was going to be easy, but as you can see from my notes here, I messed up. But I think I eventually got it. So I thought it was going to be easy, but it isn't. Okay, integral of 1 dz is just the length of the interval. So 4 minus y minus 2x. dy dx, that means x is constant. Integrate with respect to y. 4y minus y squared over 2 minus 2xy. As y goes from 0 to 4 minus 2x. Y equals 0, that's 0, that's 0, that's 0. So just plug in 4 minus 2x. I did it here at first, but I messed up. So I'm going to come back up over here. 4 times 4 minus 2x minus y squared, 4 minus 2x squared over 2 minus 2x parentheses 4 minus 2x. So you see, it started out nice. I'm integrating 1. Can you imagine how bad it would be if I had some expression in it that had said x and y and some other z stuff? It'd be much worse. It's already pretty bad. And I was originally integrating 1, right? Okay, so heavy duty algebra. Let's see, that was 16 minus 8x minus, okay, 4 minus 2x quantity squared is 4x squared. I see what I did. I put that first. 4x squared minus 16x plus 16 all over 2. That's minus 8x plus 4x squared. Okay, I distributed the dividing by 2. So 16 minus 8x, 4x squared divided by 2 is a minus 2x squared. Minus a minus 16x divided by 2 is 8x. And then minus 16 over 2 is a minus 8. Okay, then I'm trying to combine like terms. This over mark here are like terms. Negative 2x squared plus 4x squared is 2x squared. Underline 16 minus 8 is 8. And no marks. Let's see. Negative 8x plus 8x, 0. Another minus 8x. So minus 8x. Okay, so I think I finally got it. And yeah, x was going from 0 to 2. All right, so that should be it. 2x cubed over 3 minus 4x squared plus 8x from 0 to 2. Plug in 0, you get 0. Don't even bother to write it. Plug in 2. 2, 4, 8, 16 over 3 minus 4 times 4 is 16 plus 8 times 2, which is 16. They cancel out. So final answer is 16 over 3. And that pretty much does it. Okay, and yeah, let me raise it up for focusing purposes. Again, 15. And 17. 17 is a good segue into cylindrical coordinates, which we're about to start now. On that. And there's all that. And you don't need to look at my mistakes. Okay, so I am done with 15.6. Start 15.7. Okay, so what is it? 1 to 9, odd, 17, 23, odd, 29, except skip 19. Okay, so cylindrical coordinates. Triple integrals and cylindrical coordinates. From polar coordinates, we had this. Here's a picture. You may put it on your cheat sheet if you wish. X, Y, R. X is equal to R cosine theta. Y is equal to R sine theta. X squared plus Y squared equals R squared. Tangent of theta is Y over X. Okay. Leave those polar coordinates alone and then let Z be Z. So this is in the XY plane. Keep that XY plane and then just move Z as it were. So we have these equations. Don't get scared by it. These are exactly the same as these. And this is essentially saying just leave Z alone. So X is R cosine theta. There it is. Y equals R sine theta. There it is. And let Z be Z. Leave Z alone. Okay. R squared equals X squared plus Y squared. We already know that. Tan theta is Y over X. We already know that. And leave Z alone. Here's how you would find a point in cylindrical coordinates. Okay, imagine the XY plane. Forget about Z. This is the same R and theta as we had in X and Y. Okay, in the XY plane, how far away am I from the origin? There's a theta in standard position. Remember, this is the positive x-axis, right? So this region here is considered the first quadrant, right? When I go like that, that's positive x, that's positive y, first quadrant. So an angle in standard position starts off with 0 degrees or 0 radians coming this way, right? And there's theta. So here's the point R theta z. So x, y, z becomes R theta z, which is not really that big a deal because we've already done x comma y becomes R theta and just leave z alone. So here's a point in space. Here's the R, just like in polar coordinates. Here's the theta, and z is the usual vertical height. Right? We actually did a harder problem where x was the one that didn't change, and y and z got changed to polar coordinates. Okay, so we actually did a harder problem than these. For most of the problems here, z is just going to be left alone. Okay, so that being the case, we just worry about the polar coordinates part, and we've already done that. So it's really not that big a deal for a section, as it were. We integrate over a cylinder. Here's a good example, right? In the XY plane, it looks like it'd be nice to switch X and Y to polar coordinates and just leave Z alone. So this is the reason why it's called cylindrical coordinates, okay? Because it ends up looking like a cylinder. So what about the integration? Integral of f of x, y, z, dv, okay, is just what you would think. Z goes from a function of r and theta. R goes from one theta to another theta. Theta goes from alpha to beta. So that's our quote unquote favorite now. Okay, dz, dr, d theta. So when you see x, y, and z, change x to r cosine theta, change y to r sine theta. You can put this on your cheat sheet if you want. Leave z alone. dv, one of the forms of dv is dz, dy, dx, right? There's a dz. dy, dx, we know from before, is r, dr, d theta. Remember, dA can be either dx, dy, or dy, dx, or r, dr, d theta. Okay. So in a nutshell, if you change the cylindrical coordinates, change x to that, change y to that, leave z alone. Most of the time, we would like our favorite to be dz, dr, d theta, and you have to remember to multiply by an extra r. Right? Because dA, if I can cover that up, it's r, dr, d theta, right? So dz, dx, dy is r, dr, d theta. And there we go. Okay, so we can get started with some of these. The first few problems aren't really integration. They're just trying to get you comfortable with the cylindrical coordinate system. Okay, so what do we have? So we just had 1 to 9, odd, 17 to 23, odd, and 29. Then I guess at the last moment I said skip 19. I think it's because it came out too long. Number 1, plot the point whose cylindrical coordinates are given, then find the rectangular coordinates of the point. Okay, so how do you do that? 4 pi over 3, negative 2. All right, I will superscript, if we're not sure what we're talking about. For cylindrical coordinates, I'll put C. Okay. Rectangular coordinates, R. Okay. Section 8 is spherical coordinates. I will superscript with an S for spherical coordinates. Another way to pick a point in space. So this is R, theta, Z. Okay. How do you plot it? Okay, so the distance in the XY plane away from the origin is 4. Okay, so here's the point. Okay, if you can't read that, that says 4, sorry. That's 4. Here's the angle, 60 degrees in standard position. And then I go down 2. That's what I'm trying to indicate here, okay? Think of your regular polar coordinates, right? Go over 60 degrees, walk out 4 units, and then you go down 2. So that's supposed to indicate the -2 there. Okay, how do I change it to rectangular? I use the formula. X is r cosine theta, y is r sine theta, and leave z alone. So z is still going to be -2. I'm still going 2 units down. So 4 cosine pi over 3, cosine of pi over 3 is 1/2, 2. Y is r sine theta, so 4 sine of pi over 3. Okay, sine of pi over 3 is radical 3 over 2, multiplied by 4, 2 radical 3. Okay, so the point 4 comma pi over 3 comma -2 in cylindrical coordinates. Okay, and how do I get it? From an angle in standard position, move over pi over 3, 60 degrees, walk out 4 units. That's not along the x-axis. That's not along the y-axis. That's in this direction, the direction of pi over 3, and then go down 2. What is that in ordinary x, y, z? Rectangular coordinates, so I superscript with r. 2, 2 radical 3, -2. Okay. So that's the way it works. All right, and so I did A, you do B. 3D asked you to go the other way. Change from rectangular coordinates to cylindrical coordinates. Okay, so 3B looks harder than 3A. I'll do 3B. -2, 2 radical 3, 3, 3B. This is rectangular coordinates. Maybe I'll superscript with an R. Okay. Well, we already know what's not going to change. R. I'm sorry, Z. Z is still going to be 3. So how do I find R? Well, R is the square root of x squared plus y squared. So -2 squared is 4. 2 radical 3 squared, 4 times 3 is 12. Square root of 4 plus 12, square root of 16, 4. Okay, then to find the angle, well, let's see. I went -2, 2 units this way as a positive value, 2 radical 3. Hypotenuse is 4. From high school geometry, I know that the side opposite the 30-degree angle is half the hypotenuse, which means this is 30 degrees, or sine of 30 degrees is 1/2, 2 over 4. This angle here is also 30 degrees. From high school geometry, these 2 angles are called alternate interior angles. Remember anything like that? Okay. 2 parallel lines cut by transversal alternate interior angles are congruent. So if this is 30, that's 90. So I have 120 degrees, or 2 pi over 3. So there it is. R is 4, theta is 2 pi over 3, z is still 3. So the point -2, 2 radical 3, 3 in regular rectangular coordinates is now 4, 2 pi over 3, 3 in cylindrical coordinates. Okay, then they asked you some questions about what some of these things look like. 5, describe in words the surface whose equation is given. R equals 2. If we were in polar coordinates, R equals 2. Looks like this, right? Circle, center of the origin, radius of 2. Now let Z move. So you're taking this circle, moving it up and down. Z is unbounded. So you have an infinite cylinder. Mathematically, we can just say it's a cylinder. Okay. So we have x squared plus y squared equals 4, but Z is unbounded. So you have an infinite surface, basically, infinite cylinder. Cross section, Here it is, x squared plus y squared equals 4. Just take that circle, move it up and down forever, and you have this infinite cylinder. Okay. Infinite tunnel, as it were. Okay, 7. R squared plus z squared equals 4. Well, r squared is x squared plus y squared, right? So it's x squared plus y squared plus z squared equals 4. And we recognize that's a sphere, center of the origin, radius of 2. So the nice thing about the 3 dimensions is a lot of things we just proceed by analogy from what happened in 2 dimensions, right? Like here, x squared plus y squared equals 4. We just said it. Oh yeah, circle, center of the origin, radius of 2. Now add the next dimension, z squared. Sphere, center of the origin, radius of 2. But now you can go 2 units in 3 dimensions, 2 that way, that way, that way, that way, right? If it's like this, x squared plus y squared is 4, circle. So only in a plane, right? So I go 2 units that way, that way, that way, that way. You get a circle. Now add the 3rd dimension, and you get a sphere, center of the origin, and radius 2. Okay, so that's all. Okay, and then 9, write the equation in cylindrical coordinates. That's easy. So I'll do A and you do B. Okay, you leave Z alone. Change X to R cosine theta. Change Y to R sine theta. Leave Z alone. So here's one way you can do it. X squared minus X plus Y squared plus Z squared equals 1. Okay. Notice I have X squared plus Y squared. What's X squared plus Y squared? R squared. And then it says minus X, so minus R cosine theta plus Z squared equals 1. And that's pretty much about it. That's the answer. Okay, so ready to do some of the integrals. There weren't that many of them. You know, I think I'm actually going to talk about 19 since I did it, but it's just so long. Okay, so what else? 17, 23, 29. Hey, maybe I can finish the whole section today. Who knows? We'll see. All right. '17. Use cylindrical coordinates. Evaluate the triple integral over E of radical x squared plus y squared. That should be a dead giveaway, because what's the square root of x squared plus y squared? X squared plus y squared is r squared, whose square root is r. E is the region that lies inside the cylinder x squared plus y squared equals 16, between the planes z equals -5 and z equals 4. Okay, that should be a dead giveaway. Z is going to go from -5 to 4. How do you change that to polar? R is going from 0 to 4. You've got the entire circle. So theta is going from 0 to 2 pi. Okay. Let's see. So here we go. Triple integral of radical x squared plus y squared. Okay, so this thing is r, right? X squared plus y squared is r squared. Take the square root, you have r. X squared plus y squared equals 16 means r equals 4. It's a circle, center of the origin, radius of 4. Theta goes from 0 to 2 pi. Okay, so I integrate r. That r is that r. dv. dv is r dz dr d theta. Right? So there's an extra r. Don't forget that extra r. Okay, and all of these are constants. Okay, now look at how fast this integration becomes. -4 to 5, constant. 0 to 4, constant. 0 to 2 pi, constant. My integral involves r squared. Nothing to do with z. So length of the interval, 5 minus the -4, 9. Nothing to do with theta, 2 pi. See how fast it is? Okay. Theta, 0 to 2 pi, constant. R, 0 to 4, constant. Z, negative 4 to 5, constant. The only thing that's variable is R squared. So Z, there's no Z here. Length of the interval, 5 to negative 4, 9. Theta, no thetas. Length of the interval, 2 pi. So I'm just integrating R squared. So that's easy. 18 pi, R cubed over 3 from 0 to 4. Plug in 0, you get 0. Plug in 4. 18 pi divided by 3 is 6 pi times 64, 384 pi. Okay. And let's see. Yeah, you know, I think I'm going to finish this section. I have time. Finish the whole thing. Okay. And I even want to show you 19, but you'll see how bad it is. Okay. I think I said skip 19. Okay. So I'm going to show it to you. You can take notes or not, but it's a good problem. It just takes long. And by the way, some of you are saying, well, the ones you already showed us was long. That's right. This is even longer. Okay, but it's nice. So since it's nice, I'll show it to you. Okay, 19. Integrate x plus y plus z dv. E is a solid in the first octant. Okay, first octant. Underneath z equals 4 minus x squared minus y squared. Okay. Okay. Change x to r cosine theta. Change y, r sine theta. Leave z alone. dv is r dz dr d theta. Okay, so it's in the first octant. Underneath z equals 4 minus x squared minus y squared. Okay, 4 minus x squared minus y squared is 4 minus r squared. Okay, and you can think of this as 4 minus parentheses x squared plus y squared. Okay. I'm in the first octant. This is going to be a radius of 2. So r is going to go from 0 to 2, but I'm only in the first octant. Theta goes from 0 to pi over 2. Okay, so z is going from 0 to 4 minus r squared. R is going from 0 to 2. Theta is going from 0 to 2 pi. Okay. Unfortunately, all of these involve r, theta, and z, so no shortcuts. Okay, so that's when I decided, okay, I'm not going to make you do the whole thing. I'll just show it to you quickly, since some of you are probably not paying attention anyway, since I already told you I won't give you this kind of problem in the test. But let's see what happened. I integrate with respect to z. Okay, so that means, see how much I can show you here. Okay, now what did I do here? Okay, r cosine theta and r sine theta are constants as far as z is concerned. So that got an extra z. Okay. This z got z squared over 2. Okay. And z is going from 0 to 4 minus r squared. Plug in 0, you get 0. 4 minus r squared there gives you r cosine theta plus r sine theta times 4 minus r squared. It's going to be a mess. And this is 1/2 of 4 minus r squared squared dr d theta. Okay, so you can look at it or not. Say, I FOILed this all out. Came out to be that, assuming I didn't make a mistake, but I got the answer that was in the back of the book. But just show you how bad some of these triple integrals can become. Okay, 4 minus r squared squared is that. Okay, I distributed to 1/2 r to the 4th minus 4r squared plus 8. So now I have all of this mess, dr d theta. That's going to be so theta is constant. That's 2r squared cosine theta, r to the 4th over 4 cosine theta, 2r squared sine theta, r to the 4th over 4 sine theta, 1/2 r to the 5th over 5 minus 4r cubed over 3 plus 8r. That's a lot. Plug in 0. I believe when you plug in 0, you get 0. That's 0, that's 0, 0, 0. Yes. Plug in 2. 2 times 2 times 2, 8 cosine theta. 2 to the 4th is 16 divided by 4, 4 cosine theta. Put a 2 here. 8 sine theta. Put a 2 here. 4 sine theta. Put a 2 here. 16 over 5. Put a 2 there. 2, 4, 8 times 4, 32 over 3. Put a 2 there. 16. We're very fortunate that they didn't have us plug in 1. Didn't have to plug in that mess. Okay, so I'm integrating this crazy thing. And what am I trying to say over here? If I tried to combine this stuff, I got 128 over 15, I guess is what I'm trying to say there. My common denominator is 15. So times 3 times 3 times 5 times 5 times 15 times 15. So I have 8 minus 4, 4 cosine theta, 4 sine theta, and 128 over 15 d theta, right? Okay, integral of 4 cosine is 4 sine. Integral of 4 sine is negative 4 cosine, and 128 over 15 theta from 0 to pi over 2. Plug in 0, you do not get 0. That's 0, but that's going to be a negative 4. Sine of pi over 2 is 1. 1 times 4 is 4. Cosine of 0 is 0. Forget about it. Pi over 2, 128 over 15 times pi over 2 minus 4. Okay. Anyway, I got 8 plus 64 pi over 15. But this, I'm just showing it to you to show you how bad some triple integrals can get. Okay, so that was pretty bad. Okay, what time is it? 7:45. Yeah, I had 23 and 29 left. And then I think I'm done. Then I'm going to be done with the entire 2 sections. And the next time I can do spherical coordinates. Okay, 23. Find the volume of the solid enclosed by the cone, z equals radical x squared plus y squared, and the sphere x squared plus y squared plus z squared equals 2. We actually saw that theme before. Right? So bounded by these two, okay, if I square both sides, I have z squared equals x squared plus y squared. Sphere, so top part is there, cone, okay? So we got an ice cream cone kind of thing again also, right? Now, z right here, z squared equals 2 minus x squared minus y squared, or radical 2 minus r squared. Where do they intersect? Right here. Set them equal. Okay. If I set them equal, z squared equals x squared plus y squared, right? So if I change this to z squared, right here, right? X squared plus y squared, z squared. I get z squared plus z squared equals 2. 2z squared equals 2. Z squared is 1. Z equals 1. I don't have to worry about negative when they set the top part. Z equals 1. That's a circular portion. So the region in the xy plane is our unit circle, the boundary. X squared plus y squared equals 1. So again, we're asking for the volume. Okay, so again, the concept that we talked about before, okay, take this cone and the sphere, the entire volume. So it means, again, if you were to actually buy an ice cream cone, the ice cream cone is filled also, which unfortunately, when you and I buy ice cream cones, they usually don't do it that way. They're very, very nice if they pack in the ice cream here and you still got the thing on top, right? But normally what happens, they just give you that top part. They don't bother to pack it in. You can do that yourself if you want, but you know, when they hand you the ice cream, it looks the same, right? You can't tell what's there. So they figured out if it looks the same, why should we give you anything right here, right? That's the way it works. Save themselves more money. So when they give you the scoop, you know, as far as I know, nobody gives you the ice cream where it's all filled down here. But that's the volume that we're actually finding, okay? Above the cone, below the sphere. In the XY plane, it's a unit circle. So I'm integrating dV, upper minus lower. So the upper, Z, is radical 2 minus R squared. The lower is just R. Okay. The cone part. Again, the equation is Z equals radical X squared plus Y squared, the lower Z, but that's just the square root of R squared, which is R. So upper Z in cylindrical coordinates, radical 2 minus R squared, lower is R. Upper minus lower. Again, same kind of theme at the beginning of Calc 2, right? So what's the area between F and G? You integrate F of X minus G of X, upper minus lower, right? Same thing here. Upper minus lower. Upper is the sphere, the lower is the cone. We're trying to find the volume between the two. All right, so radical 2 minus R squared minus R times R dr d theta. Okay. By the way, you say, where's the Z? Z was the length of the interval, so to speak, upper minus lower. So radical 2 minus R squared minus R. Okay, distribute the R. So R radical 2 minus R squared minus R times R is R squared. Okay, this one is a substitution. Right, that's easy, R cubed over 3. Okay, I took out the 2 pi. This does not involve any theta. So length of the interval is 2 pi. So again, what happened to the Z? All of this was constant with respect to Z. So it's just the length of the interval. Upper radical 2 minus R squared minus the lower of R. Okay, so this one's easy, right? Integral from 0 to 1 of R squared dr. This one, do a U substitution. If U equals 2 minus R squared, du is negative 2R dr. So I need a negative 2 inside, negative a half outside. Okay, get this out of the way. That's R cubed over 3 from 0 to 1, 1/3. Okay, this one, I'm integrating radical U. So there's a negative 1/2. U to the 3/2 divided by 3/2 means times 2/3. Okay, so negative a half, 2/3, 2 minus R squared to the 3/2 from 0 to 1. Okay, so let's see. If I cancel this, that's negative 1/3. Plug in 1. 2 minus 1 is 1, so I have 1. Plug in 0, you don't get 0, you get 2 to the 3/2. All right, so now what did I do? I factored out the negative 1/3. There's a common factor of negative 1/3, so I put that out. So I have 1 minus 2 to the 3/2, 2 radical 2, plus 1. So that's negative 2 pi over 3, 2 minus 2 radical 2. Okay, then I just decided to clean up a little bit. Let's see, what did I do? If I distribute the negative first to get a positive, So that times that is a positive 4 pi radical 2 over 3. And then that times that is a negative 4 pi over 3. Okay, so factoring out 4/3 pi radical 2 minus 1. And that's my final answer. So what is that crazy answer? That's the total volume. Yeah, I messed up the first time. The volume here, okay, above the cone, below the sphere. So if you literally got an ice cream cone where you had this here and inside the cone was full of ice cream, then this would be the volume. Okay. Okay, 29, and then I'm done. And then I've actually bit off more than I needed to chew, so to speak. In which case I can knock off 15.7 also. Okay, so 15.8 is on spherical coordinates. I'll do that. The next time I'll give you a quiz on triple integrals, mostly just 15.6 stuff. Okay, so we would be ready to finish the chapter next week, but again, I'm not going to change the date. Okay, the date that I originally had for the exam, we'll keep that and instead just get started with our last chapter, chapter 16. Okay. 29. Evaluate by changing the cylindrical coordinates. Okay, you see they got some pretty scary stuff there. xz, dz, dx, dy. Negative 2 to 2, negative radical 4 minus y squared, positive 4 radical 4 minus y squared, and square root of x squared plus y squared to 2. Okay, if you change it to cylindrical coordinates, much, much better. Let's see why. Okay, this shouldn't bother you. Square root of x squared plus y squared, r. Right? Remember we had the formula x squared plus y squared equals r squared, whose square root is r. That's going to be from r to 2 for z. dx, x goes from negative radical 4 minus y squared to positive radical 4 minus y squared. That is simply this circle. Okay, this part right here, x is negative radical 4 minus y squared. This part here is positive radical 4 minus y squared. And then y goes from negative 2 to 2. You have this entire circle with a radius of 2 and theta going from 0 to 2 pi. Just, you can see it's really not that bad. Right, so z goes from r to 2. R goes from 0 to 2. This is the circle center of the origin, radius of 2. Theta goes from 0 to 2 pi. Okay, x, change to r cosine theta. Leave z alone. All of this junk here, dz, dx, dy, is r, dr, d theta, dz in some order. Okay, and in actuality, I wrote it this way, but yeah. What do we really, this really shouldn't be the way to write it, sorry. It should be dz, dr, d theta, but I want to emphasize here that dx, dy is r, dr, d theta. Okay, so I'm doing dz, dr, d theta. Okay, clean this up. I've got, let's see, r squared cosine theta, right? R squared cosine theta. And I'm integrating z. Z squared over 2. Going from r to 2. R squared cosine theta is a constant. Plug in 2. 2 squared is 4. Divided by 2 is 2. Minus, plug in r. R squared over 2. Dr d theta. Okay. Now, notice over here, These are all constants, 0, 2, 0, 2 pi. Therefore, I can use Fubini's theorem. This is kind of tricky. Which means instead of doing dr d theta, I can do d theta dr. So I reverse it. Okay, I've got r squared times 2 minus r squared over 2. We don't care what that is. Integral of cosine theta. Theta goes from 0 to 2 pi. That's automatically 0. So the whole thing is 0. Right? Cosine period is 2 pi. So if I integrate from 0 to 2 pi of cosine theta, it's automatically 0. There's a couple ways you can do that. Think of the graph. Right? By symmetry, we have just as much area below as above. Or if you're not convinced, just literally integrate. What's the integral of cosine? Sine. Sine of 2 pi, 0. Sine of 0, 0. Subtract, you get 0. Integral of 0. So you don't care about the r stuff. Answer 0. So there we go. Okay, I'm done with 2 sections, folks. 15.6, 15.7. Spherical coordinates next time, that's definitely a little bit harder. Okay, the cylindrical coordinates is basically just polar coordinates and then just leave z alone. Okay, so let me do my focus thing one more time, and then if anybody has any questions, you can feel free to ask it, but otherwise we're done for the day. Yeah, let me go back to here. 15.7. There's that. And all that. Oh yeah, you didn't have to do this one anyway. So what am I talking about? Well, in case anybody's interested to see how bad it was. Here it was. But otherwise, skip 19, right? We said skip 19. So I won't give you anything that quote unquote bad. 23, you don't need to look at that because I messed up. And then come up to here. And that's about it. So notice this nice shortcut. The integral of cosine theta from 0 to 2 pi, 0. Automatically, it's all 0. Okay, so Thursday, 15.8. Am I going to start any of 15.9? Maybe. 15.9 can get really long. Okay, real bad, but we'll see. We'll see. And then I'll give you a quiz on triple integrals. Okay. All right, that's it. Anybody have any questions they want to ask me? I'll check the chat quickly. Stop the share. Okay, let's see. Change the order of the variables to integrate. You can do that if you only have constants. So can I change dz, dy, dx in any order? Only do that if you have numbers. Okay, the thing you're integrating over is a box. X goes from, I don't know, -1 to 3. Y goes from 2 to 7. Z goes from -8 to 6 or something like that. Then you can change order anytime you want. That's called Fubini's theorem. But not if you have variable expressions. You're not allowed to do that. Okay. And let me check the chat. I think everybody who joined late, I got you. Okay, Kayla, I got you. Nicholas, I got you. Vin, Elliot, I got you. Min, I got you. Quiz is Thursday. No quiz today, obviously. And yeah, I think I'm caught up. Okay. What time is it? 8 o'clock? Okay. Any other questions, please? Otherwise, we'll call it a night. Okay. I don't see anything. I don't hear anything. So that's it. All right. So give you a quiz next time and we'll do spherical coordinates. All right. Good night, everybody. We'll see you all on Thursday. Okay. Bye, everybody.
Good night.
Thank you.
Thank you.
Thank you.
Good night.
Good night.